And the floor is yours, Mikel. Thanks very much.
Thank you very much. I hope the audio is not too bad. We were experiencing some clipping. Thanks a million, Joss. This is kind of a longish talk, and if some of you come up from a technical background, it will probably look a bit simple. It's basically aimed at non-specialists on language models. So I hope it's useful anyway. So here's the menu. I'm going to talk about massive language models, and some of the ingredients like neural networks and neural language models. And I will explain how they work and talk about existing models and what's the impact the language models have on our lives as professionals and not only, and then some concluding remarks. So first of all, before talking about massive language models, I will talk about the old language models. So what's a language model first? A language model, or language model is short for probabilistic language model. So it's basically a mathematical device to assign probability to a sequence of words. So ideally, if we had a good model for English, it would have to assign it would assign a higher probability or likelihood to the sentence "the chairman of the board" than to "the chairman of the cat," or it would have to assign a higher likelihood to "my cat is black" than to my blackest cat, or than to "my cat is green." So the idea is to have a model that tells you how likely a piece of text is. So the old school models are the n-gram models, and I think it's good to bring them here because they will be we will refer to them later. So n-gram models, as some of you probably know, are languages are models that compute the probability of a piece of text word by word, and they basically do that by trying to predict the probability of a word after n minus one words. So if you have a trigram model like the one here, it will probabilities have this form where this P3 stands for trigram model, and it will say what the likelihood of the word green is after the word cat is. So this is how this works. Of course, when you want to assign probability to a whole sentence, then you have to slide a window of n words, in this case 3 words, from left to right through the piece of text. So "my cat is black" has 5 items, including the period. So we start with the probability for "my" at the beginning of the sentence, then multiply by the probability of cat after "my" with some padding, which I use for the beginning of the sentence. And then when we're full into whole into the sentence, we multiply by the probability of "is" after "my cat," and the probability of "black" after "cat is," and finally the probability of the period after "is black." So basically you slide this window, pick up the probabilities and multiply them. These probabilities come from estimates. So, and these estimates are made by counting. So it's also fair to call these statistical models because they basically count how many times a sequence like "my cat" word for any word sorry, occurs for all possible words word. So these probabilities of the form probability 3 is after "my cat" are stored in a table. N-gram models only consider a context of n minus 1 preceding words. So that's not much of a context, but if you want to increase context, you have to increase n. And if you have a vocabulary of size v, and you have n-grams, you have this number of n-grams, which is v times v times v times v n times. That's a very big number, even for a small vocabulary. So you have a vocabulary of, let's say, 10,000 words, and n is a very small context of just 4 words, which is the tetragrams. Then we would have this big number of entries in the table, which is clearly unfeasible. that doesn't fit in the memory of most computers. And even, I mean, you cannot even see them in a text corpus, because to be able to see at least them once, you would need a corpus about the same size in words +3, so that you have enough for the 4 grams. So if in a new text, so you don't store all these tetragrams. So if you have a new text, and this text contains an unseen text you haven't seen before, then you have to go back and fall back to estimating the probability with trigrams, n equals 3, and if not available, you go to n equals 2, and then so on. So each time you do this, you fall back to a trigram, an n-gram, which is shorter. You lose context, and then your predictions are worse. So this was the state of the art, let's say before 2012 or something like that. N-gram models with a lot of technical improvements, but this is basically the idea. But in massive language models, what they usually call large language models, I like to call them massive, so that we get a better idea of their sheer size. I mean, the size of the n-gram is about 1,000. So the context is about 1,000. Actually, the number is usually something like 2049. And this is a very weird number, but this is because, computer people like, you see in the footnote, we like binary powers. So that's 2 to the 11th power plus 1. So it wouldn't be possible to use a table. It would not fit in the universe. There's no place in the universe with a table like that. So we cannot just build a table by counting events. We need some way to compute the probability. So we need a way to compute what's the probability of this 2049 gram word after the 2048 preceding words. So we need to be able to compute what comes after this block of 2000 words. And predicting the next word is not an easy thing. Many times it gets involved, and I will show you now, because language models, they learn to predict the word that follows a certain number of preceding words. But to succeed in that, they have to take advantage of the hints that they find in the preceding words. And I'll show you a couple of examples. This is an easy one. So this is an easy prediction. If you have the former president of the United States, Donald, that's an easy one. It should be Trump. Okay. You could even, I mean, this, you could say, oh, the system has learned it by heart. It hasn't done any processing. It's just retrieving it. But how about this? As the king only had a daughter, the next monarch, instead of a king, would be of course, we know that would be a queen. But to be able to do that prediction, we need to do some processing. And these predictions are correct predictions of a relatively small language model that you can try on even on a kind of a largest desktop machine, which is Eleuthera AI. And that model did actually produce this prediction from this context, which improves it. It implies that there's a bit of processing done with the words. But okay, I think it's fair for us to assume language models do not understand. Okay, so I would like to think that hard and to try to make sense, and this will be the point of this talk. So models don't understand, but they do things which are very clever. So without understanding, is it possible to predict the next word? So I'll run all you through an experiment, and we'll try this out. So we have this sentence, which we will have to predict the next word for. And the sentence goes, Mendivalar scares may be freighted to viniculate concision without mendic burgles. When the concision is drunk, we waskily uncle it gordle. When brunches are in costa drunk, is it uncled? What? I mean, we don't even know what the text is about. I mean, it's in English, but all of the words are just are not English, but it has English syntax, and it seems to be talking about something. And there's some discourse going on, but we don't know. There's no way to predict which word comes there. Okay, so now I'll give you some context to, like, models are trained on text. So let's see some text. So flumpet is a Mendel's function over Gödel, as brushes can also be viniculated in incursion to drunk, freighting Mendivalar scares only without burgles. Or both flumpet and Gödel freight Mendivalar scares to viniculate concision. Gödel is freighted to viniculate drunk, and flumpet is freighted to viniculate both drunk and brushes. Mendivalar scares may be freighted instead of mendic burgles to viniculate concision. So if someone is joining the talk now, it will be like, what is this about? Okay. Okay, can we, after seeing this, can we do some prediction? I mean, remember, this is about Mentivalar scares. You can freight them to viniculate concision, and there's another possibility. So maybe if you took some time, you could probably. I mean, let's read again. So there's a thing called flumpet, which is this Mendel's function. Well, see this. So if you play with this a bit, we probably don't have time, but you will have the slides at the end. I'll give you your URL. You would probably come up with an answer, and the answer is flumpet. Okay. So this, of course, is a text which I have masked some words on, and this is actually real text. So it was television. So flumpet was television. Television was a tremendous advancement over radio, as images could be transmitted in addition to sound. So I just changed. I masked some English words. But if you succeeded in thinking that probably the answer was, as here, television or flumpet in the language that I invented, you did some abstract manipulations in your mind with words that you had never heard before. Incidentally, this morning I was just reviewing the talk, and I said, hey, will ChatGPT do this well? And I just showed this to ChatGPT, this puzzle, and it solved it. Both ChatGPT and Google Bard got it right immediately. So there is nothing about understanding going on. It's more like some kind of manipulation, but it's abstract. So you have to, because if you remember, there were like tenses. So you had you could have freighting was and freighted. So you have some grammar going on too for the verb to freight, which was to use. Okay. So I don't know if the example was good, but I just wanted to show you that if you succeeded in predicting that the word was flumpet, what you did was try to understand the relationship between the words. You didn't know what the words meant, but you tried to create some abstract thing in your mind associated to the word and manipulate it to predict the next word, maybe. Or you just saw patterns in the text. That's the way we learn new words in language. So many times you encounter a word in a which you don't know what it is, but the context probably gives you enough information to learn. Okay, so the challenge is, how is this computed? Okay, how do you compute the probability of a word after a bunch of preceding words? And as I said, remember, it's not feasible to store this. We cannot store this. Even for a small vocabulary, we would have an entry. We would have a table with a number of entries that would be a 1 followed by 8,000 and something zeros. So no way to store this. So when the model sees 2048 words of text and is asked to predict the 2049th word, it cannot simply remember. It has to deduce, has to do some manipulation, as we have done a couple of minutes ago. So one ingredient is neural networks. And then why are massive language models or large language models called neural? That's because they are basically large networks of artificial neurons, and they are simulated by computers. So you don't physically build a neural net with artificial neurons, which are like, let's say, electronic devices or mechanical devices. You don't do that. You just write a computer program that simulates the works of an artificial neural net, and that's much easier because you don't have to build anything. You just run a computer program. So these neurons are such that the activation of a neuron depends on the activation of neighboring neurons and on the properties of mutual connections. And this is what happens. So this the sign and the magnitude of the weights of these connections, so because the connections have like weight or strength, um, determine the behavior of the network. Two neurons which are connected with a positive weight tend to excite and inhibit simultaneously. If the neurons are connected through a negative weights, then they tend to be in opposite activation states. So they go contrary to each other. And the effect of these interactions, of course, increase with the magnitude of or the strength of the weight that connects them. So this is a bit like friends, no? For example, if I have a very good friend, a close friend, and he's happy, I tend to be happy because we have a very strong positive connection. If he's sad, I tend to be sad or at least worried because we have positive connection. But if it's my enemy who's sad, I tell, well, if my enemy is sad, I'm happy. If my enemy is happy, I'm sad or at least worried. That's because we have a negative connection. And of course, it depends on how, I mean, if it's just an acquaintance, then it doesn't affect you so much as your closest friend or your family. So it depends on the strength of the connection. In fact, when you have a neural net and you make that neural net do some particular task, you want that neural net to have a specific behavior, a specific patterns of excitation and inhibitions. So that's the training. Training, what it does, it sets the weights so that the neural network behaves in a particular way. So there's a couple of graphs showing. So here we have neuron 4, okay, and it's getting stimuli from neurons 1, 2, and 3, which are connected to it with weights 1, 2, and 3. Okay, so the total stimulus that neuron 4 is getting from these 3 neurons is computed by just multiplying their attention, their activation state, which is S1 times W1, S2 times W2, and S3 times W3, and you just add them. So that's what we have here. So you basically add stimuli. So your final state depends on the states of the neurons around you, but it's an average or a compendium of states. We basically add them. So we add these numbers. And since these numbers can go very high and very low, and neuron states are maybe bound, you'd run them through a small function that basically makes sure that you get some maximum and minimum values, like in the graph here. So here, this would be the stimuli, the total stimulus received. So when it's very positive, like 4, you want the state to be you want the neuron activation to be the maximum, which is 1. And when the stimuli are very negative and they add to, let's say, -4, you want them to be close to -1. In the middle, you get something linear. So you get like the more stimulation, the more activation you have. But at the end, you get some saturation. This is a particular kind of neuron. It's called hyperbolic tangent neuron, but there are other kinds of neurons which have different function shapes. So this is the maths of it. And these neurons are usually put together in layers. So processing takes place in stages. So you have, let's say, this is what you would call a 4-layer neural net, which has 5 inputs, which are input signals. These are not neurons. That's why they have a different color here. And then these signals feed or stimulate the neurons on the first hidden layer. And neurons in the first hidden layer only stimulate neurons in the second hidden layer. And those in the second hidden layer do that with the third hidden layer until there's a last layer of output neurons that are stimulated by the last hidden layer. So as you see, signals are processed in stages. You input the signals here and you get an output here, but it's done in stages that happen in one fell swoop. So it's a kind of very structured or staged processing. Since we usually use a lot of these layers, not only 3, but maybe tens of them, that's why sometimes the word deep learning is used for that, because there's a deep processing of the signals in many stages. Okay, so what happens when we use these things for for language tasks? So the way it's usually done is the input signals are assigned to words in a way. So you first get your words or subwords. I'm going to be saying subwords for a few slides. I'll tell you what they are in 4 slides. Some of you probably know. But each word or each subword in the vocabulary is assigned a number. So you basically have a vocabulary with a number for each word or subword. And for example, house would get number 34. It's just an arbitrary number. And when you present a word to the network, basically all of the inputs are turned off except the one that corresponds to that word. So in the network before, let's say we had, this would be a vocabulary of 5 words only. So if you input the word number 3, inputs x1, x2, x4, and x5 would be set to 0, no signal, and x3 would be set to 1, meaning that it would get a high signal. And then processing would go on. And how do we interpret outputs? Outputs are interpreted the same way. So each output is 1 word in the vocabulary, and you interpret the outputs as probabilities. So you read the excitation of the last units here as the probability of a particular word. So depending on how high the excitation state or the activation of neuron 2 is, that would mean that word 2 has more or less probability. It's very, very simple processing. That's usually called one hot, where you basically turn off all of the units except all of the inputs except for 1, which represents your input. When you do this and you look at, let's say, for example, the first layer in the network, and you see how the neurons activate there, and you put all the numbers in a list like this, which we call a vector usually. So let's say this would be a bunch of neurons where in the first layer, after inputting a certain word, the first neuron is slightly excited like the second one, and the third one is slightly depressed, but the fourth one is very, very happy, and all the way to the last one, which is really, really happy because it's very high. And that could be the representation of the word study, for example. And when you input the word cat, then the network decides to represent cat as another vector, where the first neuron is very excited, the second neuron is very, very, very sad, and so on. So we say that neural nets represent words in a vector space. These representations are usually called embeddings. So this was, I mean, when I started neural nets, they were called representations, but now people call them embeddings because of the way they were conceived in the early 2000s. So these embeddings, these vectors, basically means that when you get a word, it gets represented as a bunch of coordinates in a vector space, like a vector. For us, it is very difficult to imagine spaces of more than 3 coordinates. So let's think about a space in 3 coordinates. So if you imagine the lexical representations of words in 3 dimensions, and you see some examples there, that would be like placing a small speck of dust somewhere in this room. So you would give 3 coordinates, like how high from the floor it is, how far from the door it is, and how far is from this wall behind me. So with 3 coordinates, you would just basically pinpoint where the speck of dust is. So similarly here, each word has its own coordinates. And one thing that happens, which is very interesting, is that words having similar semantics, similar interpretations, tend to be close to each other. So for example, pencil, pen, and eraser would be near to each other, and Spain, Europe, Italy, and France would be, the laptop and computer would probably be close to each other because they mean similar things. It's even more if you, let's say you put these vectors in as columns in a spreadsheet. You open up your spreadsheet program, you put each one of these vectors as a column, and you have one column per word. And you do some arithmetics with them. So you subtract from the column corresponding to king the column you got for man, and you add the column you got for woman. It's quite likely that the result will be very similar to the vector or to the column the network learned for queen. So this means, of course, this makes sense. If you get a king and remove him of his attributes of being a man, and you add in the attributes of being a woman, what you get is a queen, basically. And this kind of semantic arithmetic can be performed on learned embeddings. So when the embeddings or the representation learned by a neural net, when it's asked to do some language task, when you play with them like this, you get these kinds of approximations, which are very an indication that the network is actually trying to represent the relationship between words. So the semantics. So neural language models, or the massive or large language models are predictors. Of course, they predict words one by one. And this is not too different from the way your smartphone, I have to correct that. I'll make a note. The smartphone predicts the next word as you type the next message. As you type a message, so it basically predicts what the next word is, and you get three options usually, and you pick up. Usually, some of them is very often it's the one you want. So these neural language models, what they do is they estimate the probability or the likelihood P of T for each possible word or subwords T in the vocabulary that this word has to appear in the current position. So it basically tells you for each word in the vocabulary and this position, what is the probability of the word? What is the likelihood of that word? So in neural language models, this prediction process selects the most likely subwords. When you use them, you just select the most likely subword or subwords, and the likelihood of subword T at position K. So I'm getting this notation a bit involved, but pk of T, which meaning the probability of word T in position K depends on the words behind it. So this would be word K minus 1, K minus 2, and all the way back to K minus M. So mathematically, we can write this like this, and we will. I'm not going to show a lot of maths, but I just wanted to show you how it looks like. And this we have to compute. But first, let's talk about these subwords. So these models work with tokens, which are words or subwords. Okay, so for frequent words, the token is the whole word. For less frequent words, the word is split in smaller units. So you end up splitting. So here's a sentence I just copied from Wikipedia. Ran it through the through one of these word segmenters, and you'll see that words like the, an acronym, or number, or a, or of are just a single token because they are like regular words. But words like encompass is, or philosophies, or futurist are broken, or even this acronym here, which the network didn't know anything about it, was split in 5 parts. What's interesting is that the neural network will try to assign some semantics to each of these parts. So this is how it works. This segmentation is learned automatically by just running monolingual text through an algorithm, and famous ones are byte pair encoding or sentence speeds, etc. So this is like an initial step when you work with the language models, is you learn splitting. And what is this for? This avoids huge networks because the network has an input for each word. So you need to reduce your vocabulary because instead your neural network will have many words. I mean, imagine just a vocabulary of 10,000 words for English is kind of short, and English is not a very, very morphologically rich language. But now go to, let's say, a language like Turkish. You have millions of forms, so you need to be able to divide them in some ways. Okay? So the language model is basically this big black box, when it's actually not black, it's more like yellow here. And it just takes the preceding M subwords, so from tk minus M to tk minus 1. So it takes all these words, sticks it into the language model, and goes crunch, 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 computes, in layers and so on. I'll show you a little bit about how this works. And it just delivers a vector, which is a probability vector that tells me what is the probability of each word T in that position K, having seen this context of M words. And then you may try the maximum or the two highest or the three highest probabilities and select it. So the language models, basically their job is to look at a bunch of words, a block of M words, preceding words, and then generate the following word. That's all what they do. But as I tried to show you, to do this, they need to do some manipulation of the representation of words, because sometimes these predictions are not easy. For example, this is an easy one. Okay, imagine that you train a language model on bedtime stories, and the context is once upon a time, blah 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 blah, and ends in lived happily ever. What's the word that comes after that? That would be an easy one. It's just for an example. Would be after. No, lived happily ever after. That would be the end of the tale, or at least almost the end of the tale. So that's what the language model does. It reads a tale. It reads the, at least 2,000 words behind the word we have, and it just generates a word, the probabilities for what can come there. So it has to be for it to be well trained. The probability of after that context of once upon a time, blah, 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 lived ever happily ever, should be higher than the probability of before, because these stories never end like lived happily ever before. That doesn't make any sense. Or lived happily ever elephant. It's not the way they work. So ideally, what you want is that the probability predicts for after is higher than any probability for any other word T in the vocabulary. So you want to train them to produce the highest possible probability for the word you actually observe in the corpus. And that's, by doing that, the language model learns to do very intricate manipulations of semantics of words. So these calculations inside the yellow box may be performed using a variety of neural architectures, the most common being the transformer. Transformer, not the toy, that's monsters that transform into cars and things like that. So it's a transformer, and that's the citation. It's been around only for about 6 years. So, and it's not easy to explain how a transformer works, but I think I came up with a metaphor that I can use. It's only 11 slides, so bear with me. I will try to explain more or less how a transformer works, and this may be useful for for non-technical people. So here inside the box we have a transformer. So this is the transformer. This is I'm going to show. I'm only showing this to show you I have a lot. This has a lot of different processing blocks, which are neural nets, and that big blue block is repeated 12 times. So it is a very, very deep net. Sorry, some water. So how do transformer works? But first, Josh, how's audio coming? Is there still a lot of clipping, or is it working well?
No, it sounds good. I think we can hear you clearly.
Thank you.
Thanks, Mikel.
So a transformer works using a mechanism called attention. In fact, the paper, as you saw, is called "Attention is All You Need," and it applies these attention mechanisms in stages. 12 stages in the figure before, and each stage uses a set of multi-layer neural networks. So it's a rather complicated architecture. And in each stage, context is incorporated to the embedding or the representation of each token by paying selective attention to the representations of all tokens. Selective in the sense that you decide, or the network decides, which tokens to pay attention more and which tokens to ignore in the preceding stage. So in the last stage, attention is paid to all of the representation. So we have these many stages, 12 stages, as I said. And in these 12 stages, you have the representations of all of the words in the block. So you have 2014 words, and each one of them has a representation of 2014 components. So they're very, very large representations. So in each stage, you generate a new set of representations, which has improved the context. And at the end of it, you can just use this to predict the probability, as I showed you before, or you could get labels for other tasks, as I will show you in a little while. So this figure taken from a book edited by Dorothy Kenny, and we have a paper in it. The word is open access, so you can, the book is open access. So it shows, the beginning of the brown fox, a sentence starting with the brown fox with a start token. So we have a start token, and it tells you that in the next stage, apparently the representation for fox has received 15% of input from brown, and later on the representation for brown has received inputs from these other words. So each time you incorporate context, into the representations that you're going to use. So a metaphor to avoid some maths is to think that each stage in the neural net, each stage in the transformer is a generation in the history of a population. So we have a population of 2048 representations, okay? And each one at a given stage. Okay, sorry about that. I'll correct them. You'll be able to download a corrected version. Is an individual. So so we have a generation where you have 2000 individuals, and these representations use a kind of online dating service to decide who to mate with. So it's not only dating, it ends up in mating. So that ends generating representations in the next stage. So the way they generate the individuals in the next stage is by first dating other individuals in your generation and then mixing your genetic material with them. So that's the metaphor. And this metaphor is inspired on I think it's a Spanish language YouTuber, but only partly because I had to add some things, but I got a lot of inspiration from this. So how does this work? It works like a social network. So one of these online dating. So each representation offers a profile of himself to the rest of representations. And also, of course, this is how it wants to be seen. And it also generates a profile of the mates wanted. So what's the kind of mates I want? What's the kind of people I want to mate with? And that's the query. So this is like what you want. And a third vector is generated, which is the value vector, which contains the genetic material that would be combined to generate the next generation. So 3 vectors: key, query, and value. Basically, profile, what you want, and genetic material. And what the network does is, from a representation of the let me see if I can mute this. Can you mute this for me, Josh? Thank you. So using a representations query and the profile of each of the other representations, you compute a percentage of compatibility, which basically means what's the probability or what's the amount of exchange of genetic material you're going to have with that representation. So this is just to show you how complex it is, but you have, I am this one, this is the other, and I have my 3 vectors: query, value, and key, and the other has its key, value, and query too. So my query is combined with their key to generate a compatibility index. And this will be used to mix their genetic material with my genetic material. That would be the proportion of mixing, and you will get a number. And this will go on to be able to generate the next generation. So the genetic material generated is a mixture of my own genetic material and that of other representations, and the percentage in the mix is that compatibility percentage that online dating service has generated for me. So this is used to generate the genetic material. So to embody this in a neural net, the offered profiles, the percentage of compatibility, the profiles, queries, genetic material, percentage of compatibility, and representations of individuals from the genetic materials are all generated by neural networks, which are trained so that the whole transformer, the whole 12 generations of 2048 individuals, end up producing the desired outputs, which is the probabilities of each token in the next position from the inputs. So the idea is all of this technology of deciding how to mix representations and so on is basically aimed at getting a very good prediction for the next word. And in fact, everything is a bit more complicated. The process described, the mating process, occurs in 8 rounds. These are called heads in transformer parlance. So the mixture of genetic material is the result of 8 rounds of mixing, and also there is a watermark added to the representation so that you know about their position in the context window, so you know where they come from, if they were the 3rd word or the 37th word. And there are also some shortcuts in the networks which were shown in the graphic before. So the architecture is very complex, but this is the idea. So I think, well, this is just to show you that then all of these are concatenated to generate the new next representation. So now imagine we have thousands of connections, thousands of units, millions of connections, and you have to train that. So training a massive language model or large language models, as they're usually called, is not available to everyone. You need to be able to obtain, manage, clean, store, what they say, curate a corpus having thousands of millions of words of text. And then you need high performance computing facilities with GPUs, or graphic processing units, as they were called before, because they were used for graphics, for realistic graphics. And that meant doing a lot of vector operations, and this is what they do very well. So, and this is because these models, you cannot train them on a regular CPU because they're too slow. And this is the kind of operations that are very well suited for GPU. So there's a vector, matrix, tensor operations. So very involved maths, but very efficiently computed by these GPUs. When you have a model, then you can optimize it so you can execute the model in an ordinary computer sometimes. So, for example, the open model that I showed before, the Illutheory Eye, if you have a largish desktop computer, you can probably make it run. So how are these models trained? So just moving into the end of the talk. How do you train them? So the language models that you use as generative artificial intelligence, as they call it, Google, Bard, ChatGPT, and so on, are first pre-trained. And this pre-training is basically the task of predicting the next word. So you take your neural network and you show it a lot of monolingual text, and your goal is to maximize the probability assigned by the model to the word that actually comes next in the corpus. So the idea is you run the corpus, run that window of 2049 words, and you just basically ask the network to predict what's next and correct if it doesn't predict correctly. And you have to do this for all the positions in the training corpus. So the way you train them, usually you can start a neural net with random weights because you don't know which are the original values of the connection weights. So you start with the random weights, or if you have a model that had a similar task that was doing a similar job before, you can probably use those weights as a start, because maybe they contain some abilities that you need now. And the algorithm that is used for training, it basically computes how much I have to change. No, actually it does compute how much a probability of the predicted word changes for a small increase in each weight. So you basically move each weight a little bit, and you see what happens with the probability. So if the weight when you move the probability, if you move the weight up a little bit, and the probability goes up, this means you should move the weight up, because that improves your prediction. If when you move the weight up, your probability goes down, then you should probably move the weight down, because that would probably make your probability go up proportionally. So you do this repeatedly until a certain amount of time elapses. Basically, you hired, you bought some computation time on a cloud server, and that's all you can use. So you will stop before your credit is zero. Another possibility is to run the corpus a predetermined number of passes. So you just have the network read it, let's say 2 times, twice, or 3 times, or 4 times, because you know from previous experience that maybe 3 times is enough. Or when the behavior in a fraction of the corpus that you haven't used for training, but you just monitor, when the behavior in that monitor, in that development corpus worsens, then you stop, because probably you're kind of memorizing stuff. So this slide has a formula, but this is basically to introduce the concept of gradient ascent. And that's that when you change the weights, as in the formula below, you change a new weight is basically the previous weight plus the gradient, which is in the formula up, multiplied by a learning rate. And the gradient is basically the difference in the probability with the new weight and with the previous weight. By just changing weight a little bit, you divide it divide this by the size of the weight for a very small change of the delta of the weight. This is basically just to remind you, when they talk about gradient, this would be the gradient of P with respect to W. And then when you do that, you have a model that is very good at predicting the next word. But this is not what you want. You want a model that answers questions and maintains a conversation and things like this. So you retrain it on another set of tasks that are supervised this time. So you actually have to tell it, this block of text has this label. So you have a training set, which is a corpus of labeled text blocks, and you have added a special output layer to the transformer. I think there was already in the graph here in the picture. Sorry. So here there's the task classifier here. Okay. So there's not only text prediction, but you have a classifier labeler that labels the text. So we go back to the second phase, and so you basically have a corpus where you have blocks of text and labels for them, and you retrain the model so that it reproduces the labels in the training corpus. So after training it to predict the next word in the first phase, in the second phase, you ask it to produce labels for tasks like this. For example, your text block contains a premise, some delimiter, and a hypothesis, and you tell it, is this hypothesis true or false, based on that premise. So that would be an entailment task. Or you can also have a text similarity task, like you have 2 texts and you ask it how similar they are semantically. Or you can give it a context, question, and an answer, and it will tell you if the answer is correct to this question considered in this context. Or grammaticality, which is you give it a text and it tells you how grammatical it is. And for that, you use publicly available corpora that were created during previous research. So there's a particular one is GLUE, which is General Language Understanding Evaluation. It's a big benchmark of tasks. And the third phase is the one that uses human feedback. So you basically have a corpus of queries and correct answers. So you have like texts that show the desired behavior of the chatting device, of the chat, and you trained it so that the answers are reproduced. So you basically retrain the network a little bit so that the output, which is next word, next word, next word, next word, next word. So you make it a reply by just looking a response, but just looking at the next word predicted, and you make it look like the answers you want. And once you do this, you have another corpus of queries, and you run it through the trained model, and you ask it, give me n possible answers, give me n possible responses, and these possible responses are randomly sampled. So since this is a probabilistic device, it's very easy to get them to produce n answers which are representative of the output. And then you get a bunch of informants, and you ask them to rank them by value. Value could be usefulness, acceptability, could be political correctness, could be format. So some value attached to it, which is, of course, not a neutral matter. And in fact, ChatGPT was famous for hiring people in some country in Africa, I don't remember, to do this. And some of them had to go through answers, through responses that were so disturbing that they are still under very distressed after that, and with some disorder after that because of having had to review very, very disturbing content. So this was all filtered and paid at African rates, so which made it cheaper for OpenAI. And the way, so what you have these rankings, what do you do with them now? So you try to teach the network, the model, to rank itself, to see how good its own answers are. So you basically add a layer that, given a query and an answer, it generates a score, and that's called a reward model. So that reward model initially would be random. It will give you a random reward, but you train it so that the scores it generates reproduce the rankings that were given by informants. So your neural network learns to reproduce the rankings that informants would give to its answers. And with a corpus of new queries, you generate these answers, and the output of the reward model is actually used back to retune the language model. So the language model uses the reward model to retrain itself, and that reward model is informed by human feedback. That's probably the crucial part of the models that have changed them completely. This human feedback introduced into a reward model that steers the training of the neural net. So about some existing models. There are a lot of language models out there. Some of them are open and free. So this means that either your training corpus is public, or your training strategy and settings are public, so you can reproduce them. You can, or you can download the models, the models that are already pre-trained, and use them in a local machine. Or you can, and also one thing is that for them to be free, you have to be able to use them without any restriction for any application. Other models are not, so you cannot use them for free, or you have to pay, or you can use them for free or pay for them, but you cannot download them to use them on a local machine. You can download them, but there are users restrictions, or not much is known about how they train them or on which corpus. So these are secrets. This is a case of some of the most famous models. In fact, between open and free models, here's a list of some, just to mention: Eleuther AI, which are trained on a public corpus called the Pile. Other models derived from GPT-2, which is a previous model, like GPT-4All. or project like Red Pajama, which is a project which is trying to reproduce Llama, which is a model which is by Meta, and it's only allowing non-commercial use. So if you want to do business with it, you cannot just use it. So some people are trying to reproduce it in a way that it can be freely used for any purpose. ChatGPT 3.5, which is the one most of us use for free when we go into OpenAI. ChatGPT 4 is the advanced paid version, and I haven't played with it. And Google Bard, which is available to anyone with a Google account, and it's interesting competition to ChatGPT, although very different. So to get a rough idea of the size of the corpora used, this is just for you to visualize that. If you have a novel which is not too long, it has about 100,000 words. And a person can read about 200, 300 words per minute. So one person can therefore read that novel in about 7 hours. The pile, which is a small corpus, has 825 gigabytes of text, which is about 50 billion words, so 50,000 million words. And that means that's about 5 million books. So it would take a person to read those 5 million books about 35 million hours, which is about 4,000 years of continuous reading. So this is the size of a small corpus like the pile. And now, to end the talk, I want to basically reflect on the impact of these massive language models or large language models in our life, and particularly in the academic setting. Some problems first is that to train these models or to retrain them, you need to manage and store large quantities of texts, as you saw. And you need specialized and expensive high-performance computer resources. So this means that only a few companies can afford these resources and storage and computing. So this leads to centralization or gatekeeping or dependency. So we end up being dependent on a few providers of this. And that's training, but even using them requires powerful computers with sufficient memory, because these are very, very large models. So this, again, would mean that we are very dependent on whoever can afford doing this. Training and using these models uses a lot of energy and generates greenhouse gases. So, and on the one hand, so we're basically polluting the environment, and then also by building the computer facilities generated and needed to produce this, that generates toxic waste. So not only electronics waste, which is very nasty, but also just building waste. So and all of the effects of these, all of the environmental effects, greenhouse gases, toxic waste, etc., that is harder on a vulnerable society. So if you are in a rich, affluent society, probably you're not affected as much as other vulnerable people. So this is something that we have to think. And another thing is that even if you retrain and you use this human feedback and so on, so these models can still reproduce unjust biases, which are encoded in the training sets. So the training sets are real texts, and they encode a number of unjust biases, and these will show up in predicted text. Another thing is that today, today is the International Day for I think it's of language rights. I think the International Day of Language Rights, December 4th. Yeah. So that with these models, it happens that smaller languages and vulnerable groups are usually underrepresented or not represented at all. So I remember playing with ChatGPT in May, and it replied in Spanish or Catalan, which are like not so badly resourced languages, to questions I made in Occitan, which is a very, very low resource language. Even after telling it, no, you're replying in Catalan, I want to reply in Occitan, and it would just go on. It didn't really know what the difference was, probably. Another thing is that they produce natural looking new text that seems written by humans. And all of this hype about it is that now I think it's the first time in human history that we are reading articulate, very natural looking text, which is not produced by people. So since we're used to thinking that this is the output of people, we tend to think that these machines are intelligent, and we use words like artificial intelligence. I'm not gonna enter that polemic, but I think it's important to know that they're natural looking, but they also they're new. So if someone was planning on trying to see if essays turned in by students were written by ChatGPT or not, it's not going to be able to easily detect plagiarism, except for the fact that there will be so good and very, maybe a student and he or she is not capable of writing this. Well, we'll go back to assessing students in different ways now, not only just by reading their essays, because it will be laced with text coming from ChatGPT. And the third one is that text is natural, but sometimes it's wrong. So I asked, like last week, I asked the ChatGPT, does the Basque language make a TV distinction? The distinction between familiar and courteous pronouns. And he goes, no, the Basque language does not have a tu-vu distinction. Well, in Basque, and it says in Basque, there is a single second person singular pronoun, which is zu. Su. Bad, there is e and su. There are two pronouns, and there is a very clear TV distinction in many dialects of Basque. So wrong, very nicely written, but wrong. Also, it is hard to know, with this computation being distributed across thousands of neurons and millions of connections, so what's actually happening and how they make the decisions that are needed to generate a response. And some people are tempted to ask the system to explain, how did you come up with this? No? And the models produce an apparently introspective explanation, but it's just more generated text. So it's basically, they would just go and say, yeah, I did this because of that. It's just generating new text. It has nothing to do with how it came up with. It's just text that follows nicely the conversation you had. And it's partially grounded on recent context in the conversation, but it doesn't look inside itself. And as I said, massive language models will change many academic and professional sectors as they simplify or industrialize the generation of text, because they can reformulate, expand with some intention, summarize text. They can create drafts of text with a literary or artistic intent. You can ask it, write a 4-verse stanza on a subject, and it will come up with one. They can draft computer programs in many programming languages. Very, very, very interesting application, which is probably will drive many programmers out of will make them redundant, because now there's a lot of coding that can be done with the assistance of language models. They can prepare multiple choice questions from a syllabus or text. So you have a text or syllabus, and you tell it, okay, read this and prepare 3 or 4 multiple choice questions from this. May be useful. And some people even use them for grading. So you tell them, this is how I grade, this is my criteria, and this is an essay, and this would be my marks on this essay, and this is another essay, and this would be my marks. Go on with this one. Some people use that. There's even commercial applications that do that. I wouldn't, but that's what people have. So to conclude, in 1 hour and 10 minutes, more or less, neural language models generate text that is a continuation of previous text. So it's basically a continuation of the previous text, but it's maybe interpreted as an answer to a question or prompt. They are neural because they use computer simulations of the behavior of large networks of artificial networks, which are very vaguely inspired on those of animals. These models are pre-trained with large quantities of monolingual text and in a unsupervised way, just to predict the next word. And then it's fine-tuned twice, first with examples of textual tasks, like entailment or grammaticality, and then they are fine-tuned with human feedback so that they generate acceptable or useful answers. And as a result, their responses show what you would think to believe, or you would uh, tend to believe to be an intelligent behavior, because it looks like human text sometimes. But these models cannot be created by anyone, because massive resources are needed, cannot be executed by anyone, by everyone, because powerful resources are needed. And they are not transparent. We don't know how they work, most of them, and they can be unjust, and will radically change our world in the university and any sector where text production and processing is involved. So the slides are free, and you can use them following these licenses. And if you want the sources, I have them on a GitLab, so you can download them and check them out, or you can ask me for them. So you have my email there, and you get the whole bunch of slides with this QR code. So if you want to take a picture, or you want to make a note of this URL, or you can ask Joss, and he will probably have it available for you later. So thank you very much. Sorry it took a bit longer than I expected. I'm very happy to receive, to hear your questions and see and have a discussion now. Thank you.
Thank you very much, Mikel. That's wonderful. While you've said that you're going to retire in less than 2 months, I hope this won't be your last presentation for DCU after having a long connection here. Thank you very much to everyone for freighting him on your flumpet. So I'm going to stop the recording, and we can have a few questions.